At the beginning of the notebook, I structured the environments that set up clearly to ensure reproducibility. The objective of this project is to predict whether a patient has diabetes based on health and lifestyle indicators. I fixed a global random seed so that all data split and model training results remain constant across runs. This makes the notebook stable and suitable for reproducible experimentation. Given that we have the optimization window and we encourage to use AI tools, my goal was not like simply to code manually, but to use AI strategically to compare candidate models, identify performance bottlenecks, and interpretively refine the best performing approach. Today, I will walk through both the modeling pipeline and how I guided AI to improve it. I mounted Google Drive and loaded the training and test datasets directly from cloud storage. After loading the data, I printed the dataset shapes to confirm correct ingestion. After this step helps prevent silent errors such as missing columns or loading incorrect file versions. After confirming the data structure, I moved to target validation validation and distribution checks. I examined the target distribution. We have approximately 94, 805, 59 negative cases and 15 141 positive cases. This indicates a significant class imbalance. Only about 40% of the data are positive cases. This imbalance can cause the model to favor predicting the majority class, so handling imbalance became one of my first priorities. Next, I performed an 80-20 stratified split to preserve class proportions in both training and validation sets. To address imbalance, I applied smooth on the training data only. After resampling, both classes became balanced. This allows the model to better learn minority patterns and improves recall while avoiding data leakage into the validation set. After benchmarking candidate models using AI assistant experimentation, ChargeBoost showed the strongest validation AUC, giving a strong performance on structured tabular data and ability to model nonlinear relationships. I selected ChargeBoost as the primary model for further optimization. To prevent overfitting, I implemented early stopping. Early stopping monitors validation log loss and stops training when performance stops improving. This reduces overfitting risk and improves generalization performance. Rather than relying on accuracy, I evaluated multiple metrics such as accuracy, AUC, precision, recall, F1 score. The validation AUC is approximately 0.77, indicating reasonable separability. accuracy is around 73%. However, in this medical context, recall is particularly important. A false negative means failing to detect a diabetic patient, which carries higher real-world risk. Therefore, I moved beyond the default evaluation and implemented through the ratio tuning instead of using a fixed 0.5 probability cutoff. I evaluated multiple the ratios. I assigned a higher cost to false negatives compared to false positives. This transforms the classification problem into a cost optimization problem rather than a simple accuracy maximization problem. This step align the model more closely with real-world decision trade-off. To improve interpretability, I extracted feature importance from ChargeBoost. The top predictors include high blood pressure, heavy alcohol consumption, physical activity, age. This align with no medical risk factors. Interpretability is particularly important in healthcare modeling, where understanding risk drivers builds trust in the model. For the final training, I used the best iteration determined by early stopping. I retrained the model on the full dataset and generated probability predictions for the test set. The submission file was automatically formatted with correct IDs and dimensions, ensuring compatibility with the required output structure. Overall, this project demonstrated how structured experimentation, cost-sensitive evaluation, and reproducible modeling practices can form a reliable classification framework under time constraints. Thank you.